Welcome back to Differential Calculus. In this video, I want to talk about one of the strangest ideas in calculus, and that is implicitly defined functions. Let me get my head out of the way and quickly remind you that a function is a graph which satisfies the vertical line test. And yeah, we can write out the more technical definition. A function is a relationship, a rule that assigns every value in one set called the domain to exactly one set in, or one value in a second set called the range, but that doesn't really matter all that much, so I don't want to get into it. All right, so a curve that looks something like this is a function. Every vertical line passes through the curve once. We could have a function with a restricted domain so that some of the vertical lines do not pass through the curve at all. But if we have something that looks more like that, then this is not a function because a vertical line passes through the curve more than once. All right, that's something that you learned about in a previous course in algebra, pre-calculus, whatever it might have been called wherever you took it. And your instructor at the time, who might have even been me, stressed that this was vital, that you can identify when you have a function and when you do not have a function. So far in this course, everything that we have talked about has started with the assumption that we're dealing with a function and looked at things that we can do with the information in hand that we have a function we are dealing with. And so in order to proceed from here, in order to be able to actually make use of the rules that we have, we need to have functions. So if we have a graph that is clearly not a function, we need to come up with Plan B. Plan B is pretty straightforward. Let's say that we are trying to evaluate this curve at or around this point. Well, the entire graph is not a function. But what if, instead of looking at the entire graph, we implicitly assumed that we were just looking at the upper half of the graph? The upper half is a function, even though the entire graph is not. This is what we mean when we talk about an implicit function. Within this graph, implicitly, there is a function that follows the same path as the graph near the point that we care about, and then it does something at other points, or it doesn't do something at other points. We don't care what's happening at the other points. All right, taking the same graph, if instead of this point up here that we were looking at, what if we wanted to analyze the point down here? Well, in that case, we would implicitly define the function as following this part of the curve. Have the graph match up so it's the same thing in that general area, and then the rest of the graph, it doesn't matter. We don't care. All right. This is going to be a powerful tool. And yes, it completely flies in the face of all of the work that you've done in previous classes to identify when you have a function or not. But that's kind of the point. In order to realize that we need to deal with a function implicitly, the first thing we need to do is realize that what we have isn't already a function. For the rest of this video, I want to remind you, or maybe introduce you, to a couple of common graphs that are not functions that tend to show up whenever we're talking about implicit curves. They are the conic sections. Starting with the parabola, you're of course familiar with the parabola y equals x squared. That's not what I'm talking about here. I'm talking about the parabola that goes sideways. X equals y squared. Giving us a curve that looks something like that. All right, so it's just a parabola. It's turned on its side. You can use the same sorts of transforms on this parabola that you did on the normal parabolas that face upward that you learned about before. I don't want to spend too much time on that. Likewise, the circle should be one that you are at least somewhat familiar with. X squared plus y squared is equal to r squared. Plug in r equals 1 and you get the unit circle. And the circle, as I've drawn it here, or as I've defined the equation here, is centered at the origin and goes a distance r in all directions. So positive r's, some negative r's. Generalizing a circle, we have another curve called the ellipse. The ellipse is given in the form x squared over a squared plus y squared over b squared is equal to 1. And the ellipse is basically a circle, except that the radius in the x direction and in the y direction are different. The radius in the x direction is a. The radius in the y direction is b. We generally call those the semi-major axis and the semi-minor axis instead of the radius. Which one is major and which one is minor depends on which one is bigger and which one is smaller. Right? I'm not particular about the vocabulary. You don't need to know any of the vocabulary here. The only thing I'm really looking for is that you can look at an equation like this and identify that the equation you have is an ellipse. So if I have something like 9x squared plus 16y squared is equal to 144, well, as it's written, this does not look like the equation of an ellipse. But if I divide both sides of the equation by 144, and then I reduce the fractions, right? 9 over 44 is the same thing as 1 over 16. And 16 over 144 is just 1 over 9. Now it looks more like an ellipse, and I can even, if I'm thinking about it, identify that the semi-major axis is going to go to 4 and negative 4, the semi-minor axis is going to go to 3 and negative 3. Right? But I want to stress that that step is beyond what I'm looking for. I want you to be able to look at an equation like the one that's now behind my head and say, this is an ellipse. If you can get that far, I'm happy with where you are. Going beyond that, we go to Desmos. We type the equation into Desmos. Desmos graphs the equation. Desmos is also so kind as to give us clickable points that we can use to identify what the axis intercepts are. So you don't need to go through the algebra of solving those things. Desmos can handle the rest of it for you. And whenever I have a problem that's asking you to try to come up with analyzing a curve, thinking about a graph, I'm either going to provide you a graph or ask you to use computer software. I do not expect that you can graph an ellipse offhand, although if you can, it's a useful skill in a couple of different applications. What I'm looking for, again, the big idea is you see this equation, you should recognize this is the equation of an ellipse, and an ellipse is not a function. If you can get that far, you're everywhere I want you to be. All right, coming back to my notes here, I've got one more type of equation to deal with, and that type of equation is called the hyperbola. The equation for a hyperbola looks very similar to the equation for an ellipse. Except that the addition sign turned into a minus sign. And a hyperbola is kind of a shallow-ish parabola, but it mirrors itself. This particular hyperbola opens in the x direction. If I switched which one was positive and which one was negative, I would get a hyperbola that opens upward and downward. And once again, understanding what a hyperbola looks like is not the important thing. Being able to look at the equation and graph it is not necessarily what I care about. What I care about is that you can look at the equation and say, yes, this is a hyperbola, and a hyperbola is not a function. So just really quickly, I'm going to take a look at basically the same equation we had before, just taking a negative. So it'll be negative 9x squared plus 16y squared is equal to 144. Right? Very similar to the equation that we looked at previously. And in this equation, I am noticing that I have a positive and a negative between x and y. So it is a hyperbola. I am noticing that the y is the positive one and the x is the negative one. So this hyperbola is opening up and down. And then I'm turning to Desmos and I'm having it do the rest of the work for me so that I can look at the pretty picture. And so the task I'm asking of you, the video check problem in this, is going to involve a couple of equations and 3 steps. First, I want you to predict if the curve is an ellipse, hyperbola, circle, or parabola, just based on the characteristic of the curve. Then I want you to use Desmos to graph the equation and verify your prediction. As part of that, you will have to submit your graph of the equation. And I wanted to point out here in Desmos that that's actually not too hard to do, because right here, apparently I cannot quite get there. My camera cuts off before that, but there is an export button. This one, share graph. You can print it, you can export it as an image, you can use that to compile it in with the rest of your work as you are submitting these assignments. So export your image, save it somewhere, compile them all together with everything else as a part of your assignment on this one. Let's go back to the notepad and finish this off with 3 equations that I want you to graph. X squared over 5 minus y squared over 4 is equal to 8. X squared over 6 plus y squared over 6 is equal to 24. And 2x squared plus 3y squared is also equal to 24. All right, so take a couple of minutes, work through those 3 equations, see what you can do with those, and I'll see you in the next video.